Very good afternoon, friends. Welcome to the another lecture of GIT examination under Prerna scheme sponsored by All India Council for Technical Education (AICT). Myself, Professor Aasif Baig from the Department of Civil Engineering, Tulsiramji Gaikwad-Patil College of Engineering and Technology, Nagpur. So, friends, today we will see the subject fluid mechanics, in which we will cover the topic laminar and turbulent flow, flow in pipes, networks, and etc. And which is very much essential for the gate examination, which asks for 2 to 3 marks in the gate examination. So in every refining industry or oil refinery, you will see the internal flow through pipes, elbows, tees, walls, etc. And for which you have to study the behavior of flow through the pipes. So these are the objectives of today's lecture, in which we will see the understanding of laminar and turbulent flow in pipes and the analysis of fully developed flow. We will calculate the major and the minor losses associated with the pipe flow in pipe network and determine the pumping power requirements. As this, I have made another color font, because we will, due to the very less time we have, we will try to cover in a very minimum time, or we will just see, or we will look into the uh, formula part only. We will see we will see the various velocity and the flow rate measurement techniques and learn their advantages and disadvantages. So here we have introduction of the pipe flow. So we are talking about the liquid or the gaseous flow through the pipe or the ducts is commonly used in heating and cooling applications and fluid distribution network. The fluid in such applications is usually forced to flow by a fan or pump through a flow section. We pay particular attention to friction. So here the friction word is highlighted, because due to this friction there are the losses in head and the pressure is dropped. So while calculating the pumping power requirement, we have to study about the pressure drop and the head losses, which is due to the friction. So we must need to study about the friction for designing or the determining the pumping power requirement. So the friction, which is directly related to the pressure drop and the head loss during flow through the pipe and the ducts. The pressure drop is then used to determine the pumping power requirement. So here we have two diagrams for the pipe flow. One is the circular pipe and another is the rectangular pipe. And if you analyze both the pipe according to their dimension, and we study the flow through this pipe, we can conclude that the circular pipe can withstand large pressure differences between the inside and the outside without undergoing any significant distortion. And in the case of non-circular pipe, we have less results. So just theoretical discussion this was, but if you see the derivation on this, you can you must be able to identify or determine, or you can conclude that the circular section is having the good flow. So the theoretical solution are obtained only for the few sample cases such as fully developed laminar flow in a circular pipe. Therefore, we must rely on experimental result and empirical relation for most fluid flow problem rather than closed form analytical solution. So here is the equation for the pipe flow: rho into velocity average into area of that circular pipe. So in which we have to add the velocity, the density of that particular liquid which is flowing, and velocity average. So velocity average is given from this equation. So I'm just highlighting it. So this is the equation of velocity average, where we have to put at this value, and we will get the value of the average velocity. At some stream-wise cross-section is determined from the requirement that the conservation of mass principle be satisfied. So this conservation of mass, the equation we will satisfy with this equation, and this average velocity we will get from this. Okay, so the average velocity for incompressible flow in a circular pipe of radius r is given, where the average velocity is defined as the average speed through a cross section for fully developed laminar pipe flow. So V average is the half of the maximum velocity. So this is the maximum velocity here in the diagram, or V average is this one. Okay, so V average is the half of the V max. Now we will talk about the laminar and the turbulent flow, which is the requirement of this lecture. So from this flame of the wax, you can see the initial stage. We can see here. We can say this is the laminar flow, and this section is, we can say, as the turbulent flow. So laminar flow is the smooth streamline and highly ordered motion, whereas turbulent flow in which the velocity fluctuations and highly disordered motions. And in between this laminar and turbulent flow, there is another flow, that is the transition flow, which is the flow fluctuates between the laminar and the turbulent flow. So in the diagram you can see here. So here you can see the laminar flow is encountered when the highly viscous fluid such as oil flow is small pipe or the narrow passages. So, and in this case, if you inject the dye will trace, and if you find the turbulence in the flow, this is called the turbulent flow. And if you find a stream line smooth flow, this is the laminar flow. So the laminar and the turbulent flow regimes of the candle smoke, we can here differentiate these two type of flow, and from the dye we can just differentiate these two type of flow from the behavior of the dye trace. So the behavior of colored fluid injected into the flow in laminar and the turbulent flow in a pipe. So this is what the theoretical part of the laminar and the turbulent flow. And if you compare these two types of flow in the form of numbers, so we need to study the Reynolds number. So what is mean by the Reynolds number? The transition from the laminar to the turbulent flow depends on the geometry, surface, roughness, flow velocity, surface temperature, and the type of fluid. So these all the factors which we have to consider, which is affecting on the flow is either laminar or the turbulent. And by considering all this, we have to calculate the number which will be very much helpful to differentiate whether this flow is laminar or the turbulent. So the flow regime depends mainly on the ratio of inertial forces to the viscous forces. So the Reynolds number Re is the inertial forces to the ratio of viscous forces. So inertial forces is nothing but rho into V into D, where V is the average velocity and viscous forces is mu. So this is the equation which we have to use to determine the Reynolds number, and which is essential to identify whether the flow is laminar or the turbulent. So at large Reynolds number, the inertial forces, which are the proportional to the fluid density and the square of the fluid velocity, are large relative to the viscous forces, and thus the viscous forces cannot prevent the random and the rapid fluctuation of the fluid turbulent. So at small or the moderate Reynolds number, the viscous forces are large enough to suppress this fluctuation and to keep the fluid in the laminar flow. So the critical Reynolds number Re, the Reynolds number at which the flow becomes turbulent, the value of the critical Reynolds number is different for different geometries and flow condition. The Reynolds numbers can be viewed as the ratio of inertial forces to viscous forces acting on the element. So for flow through the non-circular pipe, the Reynolds number is D equals to 4AC divided by P. So which is based on the hydraulic diameter. So the hydraulic diameter DH, equals to 4AC divided by P is the defined such that it reduces to ordinary diameter of the circular tubes. So while we have to calculate the Reynolds number, from non-circular pipes, you have to use this equation. So for flow in a circular pipe, Reynolds number should be less than, if it is less than 2300, so it is laminar flow, and if it is greater than 10,000, then it is turbulent flow, and it is in between 2300 to the 10,000, so then it is the transition flow. So we will see the entrance region. The study of this entrance region is also essential. So velocity, boundary layer, boundary layer region, and irrotational flow region. These three basic things which we have to study in this topic. So what is mean by the velocity boundary layer? The region velocity boundary layer, the region of the flow in which the effect of the viscous shearing forces caused by fluid viscosity are felt. Where boundary layer region, the viscous effect and the velocity changes are significant, and irrotational flow region, where the frictional effect are negligible and the velocity remains essential constant in the radial direction. So in the diagram you can see the velocity boundary layer, irrotational core, and the fully developed velocity profile and developing velocity profile. So this velocity profile here in this pipe you can see these three things. Okay, so velocity boundary layer region, and irrotational flow region. So this is the hydrodynamic entrance region. This region is the hydrodynamic entrance region, and this is the developed region. Okay, so the development of the velocity boundary layer in a pipe, the developed average velocity profile is parabolic in laminar flow, but somewhat flatter or fuller in turbulent flow. So hydrodynamic entrance region is the region from the pipe inlet, the point at which the boundary layer merge at the center line. Hydrodynamic entry length LH, the length of the region. Hydrodynamically developing flow is the flow in the entrance region. This is the region where the velocity profile develops. Hydrodynamically fully developed region is the region beyond the entrance region in which the velocity profile is fully developed and remain unchanged. And what is meant by the fully developed is when the both the velocity profile, the normalized temperature profile. So hydrodynamically fully developed region is determined from this derivation. So in this fully developed flow region of the pipe, the velocity profile does not change downstream, and thus the wall shear stress remain constant as well. Now from this figure, we can see that the pressure drop is higher in the entrance region of pipe, and the effect of the entrance region is always to increase the average friction factor for the entire pipe. So it is the entrance region. Here you can see in the diagram, I'm just highlighting it. This is the entrance region. So in the entrance region, we can see there is a higher drop in the pressure, where it gets in the streamline in the fully developed region. So the variation of wall shear stress in the flow direction for flow in the pipe from the entrance region into the fully developed region. So entry length, we will see the hydrodynamic entry length is usually taken to be the distance from the pipe entrance to where the wall shear stress, and thus the friction factor reaches with about 2% of the fully developed value. So here is the equation where LH is hydrodynamic entry length for the laminar divided by D. It should be equals to 0.05 Reynolds number. So hydrodynamic entry length for for laminar flow it is given. So, and for the turbulent flow it is LH turbulent divided by D equals to 1.359 Reynolds number to the power 1 by 4, and LH turbulent divided by D should be equals to or nearly equals to 10. So the pipe used in practice are usually several times the length of the entrance region, and thus the flow through the pipe is often assumed to be fully developed for the entire length of the pipe. The simplistic approach gives reasonable result for long pipes, but sometimes poor result for short ones, since it unpredicted the wall shear stress and thus the friction factor. We will see the laminar flow in pipe. We consider steady laminar incompressible flow of a of a fluid with constant properties in the fully developed region of a straight circular pipe. In fully developed laminar flow, each fluid particle moves at a constant axial velocity along a streamline, and the velocity profile remains unchanged in the flow direction. There is no motion in the radial direction, and thus the velocity component in the direction normal to the pipe axis is everywhere zero. There is no acceleration since the flow is steady and flow table. So here is the equation where we can see the free body diagram of a ring shaped differential fluid element of radius r, the thickness dr and the length dx oriented coaxially with a horizontal pipe in a fully developed laminar flow. And if you derive, we will find the equation as dp by dx equals to minus 2 tw by r. So where we will see the equation for the maximum velocity S2 into V average. So from the earlier statement, we can say that the velocity average is the half of the velocity maximum. So the free body diagram of the fluid, this element of the radius R and the length dx in fully developed laminar flow in a horizontal pipe. Now, pressure drop and the head loss. A quantity of interest in the analysis of pipe flow in the pressure drop del P, since it is directly related to the power requirement of the fan or pump to maintain flow. We know that dP by dx equals to constant, and integrating from x equals to x1, where the pressure is P1 to x P1 to x equals to x1 plus L, where the pressure is P2 gives del P by dx equals to P2 minus P1 by L in the laminar flow, where del P equals to P1 minus P2 equals to 8 mu L V average divided by R square equals to 32 mu L V average divided by D square. So a pressure drop due to the viscous effect represent an irreversible pressure loss, and it is called pressure loss, that is denoted as del PL. So del PL equals to FL rho V square divided by D. So it is D by 2 actually. So we can write this as pressure loss for all types of fully developed internal flows. While in the case of circular pipe laminar flow, it is 64 divided by Reynolds number. So here are few equations for Darcy friction factor. Darcy friction factor. One equation is given for the head loss. So head loss, we are writing it as H subscript L equals to del P L divided by rho G equals to FL by D V square average divided by 2G. So in laminar flow, the friction factor is a function of Reynolds number only and is dependent of the roughness of the pipe surface. The head loss properties represent the additional heights that the fluid needs to be raised by a pump in order to overcome the friction losses in the pipe. So here for the horizontal pipe, equation for Poiseuille's law is given. So this is somewhat is not much important for this part, this topic. So we will skip this, and we will see the equation. The pressure drop del P equals to the pressure loss del PL in the case of a horizontal pipe, but this is not the case for inclined pipe or pipe with the variable cross sectional area. This can be demonstrated by writing the energy equation for steady incompressible one-dimensional flow in terms of head as rho P1 by rho g plus alpha 1 V1 square divided by 2g plus Z1 plus H pump. So where it is H is the head loss equals to P2 divided by rho g plus alpha 2 V2 square divided by 2g plus Z2 plus H turbine plus head loss. So from this equation we can calculate the head loss. So therefore the pressure drop del P equals to P1 minus P2 and the pressure loss del PL equals to rho GHL for a given flow section are equivalent if one section, the flow section is horizontal so that there are no hydrostatic or gravity effects. So Z1 equals to Z2. So the flow section, they change the fluid. The flow section does not involve any work devices such as pump or turbine. Since they change the fluid pressure and the cross-sectional area of the flow section is a constant, and thus the average value velocity is constant. V1 equals to V2. And the fourth one is the velocity profile at section 1 and 2 are the same shape. So here we can see the effect of gravity on the velocity and the flow rate in the laminar flow. So for we are seeing the free body diagram of a ring shaped differential fluid element of radius r, thickness del r, and length dx oriented coaxially with an inclined pipe in a fully developed laminar flow. So here is the equation for the gravity effect on the velocity and the rate of the laminar flow. So laminar flow in circular pipe, we can conclude this topic in these few points. Fully developed flow with no pump or the turbine in the flow section, that is del P equals to P1 minus P2, and for horizontal pipe velocity is del P pi d raised to the power 4 divided by 128 mu L, and for inclined pipe it is del P minus rho GL sin theta pi d raised to the power 4 divided by 128 mu L. So the relations developed for fully developed laminar flow through horizontal pipes can also be used for inclined pipe by replacing del P with the del P minus rho GL sin theta. So here are the laminar flow in the non-circular pipe. So in the case of non-circular pipe, the friction factor F relations are given in table. For fully developed laminar flow in pipe of various cross section, the Reynolds number for flow in this pipe is based on the hydraulic diameter, that is del H equals to 4 AC divided by P, where AC is the cross sectional area of the pipe and P is the weighted perimeter. So this is the table which is given, where the value of friction factor F is given in this table depending upon the shape of the pipe. So you can take the screenshot of this. If you're done with this, let me know. Okay. Thank you. So these are the example for laminar flow in horizontal and inclined pipes. We will just move ahead because this is not much essential right now, and we have to cover the topic which is very large in the contour. So we will see the turbulent flow in pipe. So turbulent flow, which is most flows encountered in the engineering practice are turbulent, and thus it is important to understand how turbulence affects wall shear stress. Turbulent flow is a complex mechanism dominated by fluctuations, and it is still not fully understood. So turbulence flow is characterized by disorderly and rapid fluctuations of swirling region of fluid called eddies throughout the flow. These fluctuations provide an additional mechanism for momentum and energy transfer. In turbulent flow, the swirling eddies transport mass, momentum, and energy to the other region of flow much more rapidly than molecular diffusion, greatly enhancing mass, momentum, and heat transfer. As a result, turbulent flow is associated with much higher values of friction, heat transfer, and mass transfer coefficient. The intense mixing in the turbulent flow brings fluid particles at different momentum into close contact and thus enhances momentum transfer. Now from the figure we can see water exiting a tube in A figure, laminar flow at low flow rate, in B turbulent flow at high flow rate, and C same as B but with a short shutter exposure to capture individual eddies. So here is the equation for the velocity. The laminar component account for the friction between layers in the flow direction, and in the turbulent component according for the friction between the fluctuating fluid particles and the fluid body related to the fluctuation component of the velocity. So here we can see this, we can study the velocity change in a case of the laminar flow and the turbulent flow. So the fluctuation of the velocity component u with time at a specific location in the turbulent flow, the velocity profile and the variation of shear stress with radial distance for the turbulent flow in a pipe. So here is the turbulent shear stress. Turbulent shear stress is nothing but the minus rho into u and uh, rho. Turbulent shear stress, the terms such as minus rho uv or minus rho u square are called Reynolds number. Reynolds stress and turbulent stress. So from the figure of the velocity, fluid particles moving upward through a differential area dA as a result of the velocity fluctuation. So this is the turbulent flow and the laminar flow velocity diagram, which indicates the molecular diffusivity of momentum v as well as rho as well as mu is a fluid property, and its value is listed in a fluid handbook. AD diffusivity V denoted as Vt as well as mu t, however, is not a fluid property and its value depends on the flow condition. AD diffusivity decreases towards the wall, becomes zero at the wall. Its value ranges from zero at the wall and to several thousands times the value of the molecular diffusivity in the origin. The velocity gradients at the wall and thus the wall shear stress as much larger for turbulent flow than they are flow as laminar, even though the turbulent boundary layer is thicker than the laminar one for the same value for the free stream velocity. Now, what is the turbulent velocity profile? The very thin layer next to the wall where the viscous effects are dominant in the viscous sublayer. So the viscous sublayer, which is also called as the laminar or the linear sublayer. The velocity profile in the layer is very nearly linear and the flow is streamlined. Next to the viscous sublayer is the buffer is the buffer layer in which turbulent effects are becoming significant, but the flow is still dominated by the viscous effect. Above the buffer layer is the overlap or the transition layer, also called as inertial sublayer, in which the turbulent effects are much more significant but still not dominant. Above that is the outer layer that is called as turbulent layer in the remaining part of the flow in which turbulent effect dominate over molecular diffusion. So from this figure we can understand what is the buffer layer, what is the viscous layer, what is the overlap layer, and what is the turbulent layer. So this section is identical for identify these four types of layer. Now the velocity profile in fully developed pipe flow is parabolic in laminar flow, but much fuller in turbulent flow. Note that velocity, that is UR in the turbulent cases, is the time average velocity component in the axial direction. So this is what the equation is given for the friction velocity, law of the wall, and the viscous length. So this is the thing which is not much important for now. So this is the Moody chart. You can Take the screenshot of this. Now, these are the observation of the Moody chart. Just I am reading this. For laminar flow, the friction factor decreases with increasing Reynolds number, and it is independent of the surface roughness. The friction factor is a minimum for a smooth pipe and increase with roughness. The Colebrook equation is, in the case, reduces the Prandtl equation. The transition region from the laminar to the turbulent region is indicated by the shaded area in the Moody chart. At small relative roughnesses, the friction factor increases in the transition region and approaches the value for the smooth pipe. At a very large Reynolds number to the right of the dashed line on the Moody chart, the friction factor curves corresponding to the specified relative roughness curves are nearly horizontal, and thus the friction factor are independent of the Reynolds number. The flow in the region is called fully rough turbulent flow or just fully rough flow because the thickness of the viscous sublayer decreases with increased Reynolds number, and it becomes so thin that it is negligible or small compound to the zero. So these are the type of fluid flow problems: determining the pressure drop, determining the flow rate, and determining the pipe diameter. So these three types of numerical are in the examination. We will skip this numerical part. Just remember the equations. Now we will see the minor losses. So the minor losses, the fluid in a typically pipe system passes through various fitting, walls, bends, elbows, tees, inlet, exits, enlargement, and the contraction in addition to the pipe. So all these affects the minor losses. So one is the loss, major loss. Major loss is due to the friction, and minor losses is due to this type of fitting in the pipe. So this component interrupt the smooth flow of the fluid and cause additional losses because of the flow separation and the mixing they induces. In a typical system with long pipe, these losses are minor compared to the total head loss in the pipe, which is the major loss, and are called as minor losses. So the equation for the minor losses is V square by 2G. So head loss due to the minor, it is del P L, that is the losses in pipe length divided by rho into G. So for a constant diameter section of a pipe with a minor loss component, the loss coefficient of the component such as gate wall shown is determined by the measuring the additional pressure loss it causes and dividing it by the dynamic pressure in the pipe. So from the figure you can see the minor losses due to the wall body in a long length pipe. When the inlet diameter equals outlet diameter, the loss coefficient of the component can also be determined by measuring the pressure loss across the component and dividing it by the dynamic pressure. The equation is given, constant for this type of problem. So when the loss coefficient for the component is available, the head loss for that component is HL equals to KL divided by 2G. And minor loss are also expressed in terms of equivalent length. So it is HL equals to KL divided by 2G. The head loss caused by a component such as the angle wall shown is equivalent to the head loss caused by the section of the pipe whose length is equivalent to the length. Now this is the total head loss in general. The equation is given. And the final equation is we have found as F, that is the friction factor F into L by D plus sum of KL into V square divided by 2G. So the head loss at the inlet of a pipe is almost negligible for a well-rounded inlet, but increase to about 0.5 for sharp edge inlet. So these are the various conditions where the minor losses occurred, and according to which the various loss coefficient is given. So you can take the screenshot of this. Take the screenshot of this as well, and let me know when you ended with the taking the screenshot. take the screenshot of this case also. Thank you. So these are the deep knowledge about the minor losses. So due to the time constraint, we will stop here and we will open this session for the question answer. If you have any question, please feel free to ask.